Okay, this is the fifth video in a five-part series in determining the volume of a rotated solid. So since this is part 5, if you haven't seen any of the previous parts, I would recommend you go through these in order because math, when we learn something new, it's not really new. It's just built on something that we already understand and know how to do, and then we just build on that. So this one, we're going to go through 3 or 4 problems fairly quickly, and we're going to compare our disk and shell methods. And the way we're going to do that is we're going to evaluate the integrals on a calculator, even though you will be, in your classes, you will be held accountable to be able to work through the process of integration by hand as well. Just to speed up time, we're going to do it on our calculator, and I am going to do this kind of quickly. So if you get kind of like lost, remember you're on a computer or a phone or something like that, so you can pause at any time just to kind of mentally catch up. So here we go. First one we're going to take a look at, and we've already done all of these using either the disk washer or the shell method at some point through this video series, but now we're going to just compare the two. So see what's happening here. We're taking this region and we're going to rotate it around the y-axis. So let's start out with the disk method. We'll look at that one, and then we'll compare that to the shell method, and we'll compare that. So imagine that with the disk and washer, we're picturing what's happening. This is a complete solid. There is not a hole gouged out of the middle of this, so it's going to be a single disk method, not a double disk. And imagine those disks. I'm pinching a disk, and that's a dy question. Okay, so I'm going to set it up as pi r squared times the height. And so what is the radius of each one of these disks? It looks like the radius is whatever the x value is every time. So I cannot write x there. So what is x equal to? We've done it a lot, right? X is equal to the square root of y. So and it's over the interval from 0 to 9. So if I clean that up a little bit, that nicely, square and the square root cancel. So we have an integral pi from 0 to 9 of y dy. All right, so we'll check that answer out here in a second. Let's look at the shell method. You have to kind of change your line of thinking here a little bit, because now these shells are being rotated around the y-axis. And look, pinch that shell. That's an x value. So I'll draw that shell out because it's a little more difficult to comprehend the shell method than the disk method. So imagine that shell rotating around. And so the setup here is the circumference, so 2 pi r times the height, and we just said it's dx. So what's the radius of each one of these shells? Like here, that's one shell cross section, okay? Its radius looks to be whatever the x value is. And this shell out here that wraps around a little further, its radius from the axis of rotation to where the function is another x value. So 2 pi r, and what's the height of each one of these? Uh-oh, look. So here is the x and y, xy. This is the y value right here. This is going to be 9 minus the y value is the height of that shell. So I'm going to write 9 minus, well, I can't write y there. What is y? Y is x squared. And we're evaluating that over the interval 0 to 3. All right, so let's see how this turns out here. So we're going to go the integral from 0 to 9. I'm going to hold off on the pi till the end. Okay, so I'm going to, and this says y dy, but evaluating the integral x dx is the same thing. And so I'm saying the answer to this one is 40.5 pi. Okay, saving the pi till the end. All right, on this one, we're going to evaluate this integral. I'm going to save the 2 pi till the end. So 0 to 3 this time. And I could either type that in as I see it using parentheses, or I can call that 9x minus x cubed. I'm going to do that, 9x minus x cubed dx. Okay, and remember I'm going to have to multiply that by 2 and then pi at the end of this. So here's the integral. I'm going to multiply it by 2, there it is, 40.5, and then pi. Comparing two totally different methods, disk method, single disk method, shell method, same identical volume, which we should get. All right, let's take a look at the next one here. All right, so we're going to take this bounded region and rotate it. Remember how I changed it in the last video? X equals -1 is this vertical line right here. So definitely if we're using the disk washer method, there's a hole gouged out of the middle there, so it's a double disk. So I'm going to set it up as so. So we're going to say pi r squared. Now let's pinch that disk to dy minus pi r squared dy. Okay, we did this one in the third video, so I'm going to get through it pretty quickly here. The outside radius, the big radius, is constantly 4. The inside radius is 1 plus the x value. 1 plus the x value. So I'm going to write 1 plus x. And we're evaluating that over the interval 0 to 9. Okay, let's see. Shell method here. Let's set it up. Let's picture that shell being wrapped around, and that's a dx. So here we go, 2 pi r. 2 pi r, the height and the thickness of each shell is a infinitesimally small value for x. And I'll put in the interval from 0 to 3. So let's see. Here's one of the shells. It's wrapping around. What's its radius every time? It looks like it's going to be 1 plus whatever the x value of the function is. And what's the height of each one of these? It is the y value of the function. I'm not going to write y there, I'm going to write y. Okay, so there's our integrals, and let's check it out again here. So we talked if it's the same variable and same interval, we can combine the two. So I'm just going to do that. And I'm going to say I could say 16. I'll say 4 squared minus the quantity 1 plus radical x, that quantity squared dx, and I'm going to multiply the pi in at the end here. Let's see what that is. It's thinking a bit. 50. Our calculators, remember, don't know calculus. They're just adding up. They're adding up values, and we can say that we can assume that that exact answer is going to be 58.5 pi. Let's see what happens with the shell method now. I'll save the 2 pi till the end. And I could either type it in as is. I'm just going to distribute and say x squared plus x cubed. And then at the end I will multiply in the 2 and the pi. So times 2, there's our 58.5, and times pi. All right, let's take a look at the next one here. This region around the axis of x equals 3. So as we rotate this, I'm seeing a complete solid. So it's not double disk, it is a single disk. So also imagining those disks. Okay, so that's a dy again. So pi r squared dy. And we did this one earlier. Remember that the radius of each of these disks is going to be 3 minus the x value. So 3 minus x. What's x? There's 3 minus x. And over the interval 0 to 9. Shell method. Let's set it up. The shells. Here's one of the shells right here. This is going to be a dx. So 2 pi r height dx. Now what's the radius? The radius is going to be 3 minus the x value. Gets us that distance right there. So 3 minus x. Here I couldn't write 3 minus x. Here I can. And what's the height of each one of these shells? It's going to be the y value, x squared. Okay, and this is from 0 to 3. So let's compare these two. So we have integral 0 to 9, and we have the quantity 3 minus the square root of x, that quantity squared, and times pi. Let's see. That's going to be 13.5 pi. And this one, 0 to 3, and go ahead, yeah, 3x squared minus x cubed. 3x squared minus x cubed dx. And then I will multiply the 2 and the pi in at the end. All right, I try to keep these under 15 minutes. I don't know exactly where I am right now, but we're going to do one more because we can. All right. So this time we're taking this region and rotating it around this line down here, y equals -2. So disc washer, definitely a hole. We did that earlier. If you want to go back to video 3, it's there. It's that volcano that we thought about that's kind of on its side. So we're going to take pi r squared. Let's see, what is that? Okay, so here's a disk method that's dx. So pi r squared times the height minus pi r squared times the height. So let's get the big radius here. The big radius is 2 plus the y value. 2 plus the y, it varies. 2 plus this y value. 2 plus the y value. And the small radius is a constant 2. And since it's dx, we're going from 0 to 3. All right, let's take a look at shells. Shells are wrapping this way. Look at that. Pinch that shell. Its thickness is dy. So here's the setup. 2 pi r gets us the circumference times the height, and we said this is dy. So I'm going to just write that in as we go. So here's this one of the shells coming out of the paper here. What's its radius length? It's going to be 2 plus the y value. Each shell, right? Even this one up here. 2 plus its y value. So I'm going to write 2 plus y. What about the height of each of these? It's this way as the height. So we're going to have to, right, because here's x, here's y, here's the x value. 3 minus the x value. So 3 minus x. There it is, 3 minus x. And we're going from 0 to 9. All right, let's compare again. So let's see. Honestly, I don't think I could multiply the, or write as 4 plus 2x squared plus x to the 4th, but let's change it up here. Let's just keep it in its quantity here. And I'll combine these two. So we're going to have 2 plus x squared, that quantity squared, minus, I could say 2 squared. I did that earlier, I think, with one of the radii. I didn't square it. Or I could just say, well, I know 2 squared is 4, so I'm just going to write that in as is. So let's just double check. That looks good. That looks good. 0 to 3. And I'm going to multiply the pi in at the end. And we're looking at 84.6 pi cubic units, whatever those might be, inches, feet, meters. And let's look at the next one here. I'll multiply the 2 pi in at the end. I could distribute these, but I'm not. You don't have to. Does that look good? Radius, height, all in terms of x, and I'm going to multiply that 2 and pi at the end. Oh, that one's taking a while, it's thinking. So times 2, there's that 84.6 times pi. Okay, hope this series was beneficial for you, and until next time.